Hello everyone, welcome to this video. In this video we are going to look at few of the examples of group. So let's start with our first example here. In the first example we consider the set as the set of integers and the associated operation, which is a group operation, that is addition. We need to check whether this is a group or not. So in order to check whether a mathematical quantity, that is a set given with a binary operation, is it a group, for that we need to check the associativity. First of all, we need to check the closure. By checking the closure, you are checking that whether this operation is it a binary operation or not. The next thing that you require to check is that of associativity, right? Another thing is checking the identity. Is there an identity present in the group which is unique? And next, finally, you have to check whether we have an inverse for each of the element which is a member of the given set. If that is so, if all these properties satisfy simultaneously, then the given set together with this binary operation, that will form a group, right? So now in this case, in the first example, we are saying we consider either you consider the set of integers, or you consider the set of rational numbers, or you consider the set of real numbers. In each of the three cases, if you are given the operation of normal addition, then they form a group. Why? Because you know addition is additive in nature. If you add two numbers a plus b, then you are going to get another number c, which is also, in case of integers it is integer, in case of rationals it is rational, and in case of reals it is real, right? Next, you will check the associativity property. So that means you will check a plus b plus c, is it equal to a plus b plus c? So that this is true in case of addition. You know, there is no difference if you take these two elements first or these two elements first. So we have associativity for addition as well. Now what is the identity here? The identity in case of addition is 0. So that means if you add 0 to any number, you will get back the number again, right? So this is the additive identity in all the three cases. And what is the inverse here for each element? Suppose you take an arbitrary element a, then what will you add to this particular element in order to get the identity which is 0? So the answer is obviously minus a, right? If you add a to minus a, then you will get 0. So therefore in this case, and a is some arbitrary element. If you take 1, its inverse would be minus 1. If you take 2, its inverse would be minus 2, and so on. So therefore for every element which is a member of integer, we have an inverse. Similar is the case for rational number. Suppose we are taking 5 by 4 as the given rational number. So what will you add to this rational number in order to get a 0, which is the identity? So you will add minus 5 by 4 to it, right? And same is the case with real numbers, correct? So moving further to our next example here. In the next example, we are taking the set as a set of integers and the binary operation as multiplication. So I am saying this does not form a group, although you know multiplication for integers, a multiply with b multiply with c, this is equal to a multiply with b first and then with c, right? So therefore we have the property of associativity. In this case there is no issue, right? And moreover, we also have identity in each case, but the problem arises when we take the inverse of the element. So for an instance, if you take the element 5 here, this element 5 does not have an inverse in integers. Why? Because for the multiplicative identity, we have the element 5, operation is multiplication, and we are looking for this particular element so that it is equal to 1. And this element should also belong to our given set, the set of integers, correct? So here obviously the thing that comes to your mind is the answer is 1 by 5, but 1 by 5 is not a member of the set of integers. Instead it is a member of the rational numbers, correct? So therefore for every element we do not have an inverse in the set of integers, so it is not a group. Moving further, let's see this example. Suppose we are having the set containing 4 elements. So now this is a finite set, right? Because it contains only finite number of elements, which are 4 in our present case. So the elements are 1, -1, iota and minus iota, and the operation here is complex multiplication. Why complex multiplication? Because you see we have complex numbers also present in our set. For this set and for this operation, we wanted to check whether it forms a group or not. So for group, we need to check that first of all the closure property holds or not. So you need to check if you multiply two numbers from this group under complex multiplication, does it give you the same element back from the set? Yes, it is so. So therefore in this case we say the closure property holds. The similar is true when you take any two other elements. So you have minus iota square, which is equal to minus of -1, which is equal to 1, correct? So therefore this one is also a member of this set, so therefore we have the closure property. Again, associativity holds for multiplication in complex numbers, that you already know from the basic study on complex numbers, correct? So we have the two properties. Next we have to identify the identity of the group. So for that what we do, to have a better picture, we just create this table. Remember I've told you about Cayley tables. So this is one of the Cayley table for this set together with this operation. So we write the operation here, we write the elements here, and we write the elements here in the same order. Now we have to see what do you obtain when you have 1 star with 1. So we are multiplying 1 with 1 because here the operation star is multiplication. So you have 1 into 1, that is 1, 1 into -1 is -1, 1 into iota is iota, 1 into minus iota is minus iota. Then you have -1 into 1 is -1, -1 into -1 is 1, -1 into iota is minus iota, -1 into minus iota is plus iota. Similarly you can fill out these two rows also, right? So this is the table that we obtain in this case. This is the Cayley table. Now according to this table we have to see that which element give you all the element back. So if you take any element A from the given set, right, so we are looking at the element such that when you multiply this element with some element, you are getting back the element itself, right? So we are calling this element as the identity. So what is that element? So you could pretty well know it from this table. So from here you see you have 1 here. If you multiply this 1 with 1, you are getting back 1. This is same as this, this is same as this, this is same as this, and this is same as this. So that means this 1 is acting as an identity here in this case. So you can write it here, and the same thing happens here. When you see you have a 1 here, you have a -1 here, you have iota here, you have minus iota here. So that means this one does not create any difference to whatever element that is present over here. So that means 1 acts as identity from this side also. So that means you have A into 1 is equal to A, and moreover you also have 1 into A is equal to A. So this is the identity and it holds for this group, and we have it as the number 1 from the given set. Now we have to look for inverse of each of the element. Does it exist for each of the element? So let's see one by one. The inverse of 1, the inverse of -1, iota and minus iota. That is what we are looking for. So you see we are looking for a number here such that when we multiply it with 1, we are getting back 1. So what is that number? When you multiply 1 with something, you are getting 1. So what is that something? That is 1. So the inverse of 1 in this case is 1 only. So see, in a similar manner we can have the inverse of -1. So by what number you multiply by this one, so that you get the this multiplicative identity of the group, that is 1. So you see, if you multiply, this is a -1. Where do you have 1 as the answer? 1 is the answer. So by what number you have to multiply? You have to multiply it by -1. So here the inverse is -1. In a similar manner, we are looking for the inverse of iota. So that means by what number do we multiply iota so that we have the additive identity as 1. So let's look at iota here. by what number should we multiply it so that we have the answer as 1. So this is the answer, which is 1. It corresponds to minus iota. So if you multiply iota with minus iota, you will get back 1. In a similar fashion, you see you have minus iota here. If you multiply minus iota with iota, then you will get back 1. So therefore in this case, inverse of minus iota is iota. So therefore this forms a group under complex multiplication. The next example is that of the set of positive rational numbers. So all the rational numbers which do not contain 0, or which in fact they contain 0, no, they do not contain 0, because we are not saying non-negative, but we are saying positive rationals. So for positive rationals, what we are saying all those rationals which are positive, they are contained in this set, and we are calling it to be the set Q positive, right? So for this set, we are defining the operation of multiplication. Now we have to check whether this is a group or not. So this is a group. Why? Because the closure property holds for rationals under multiplication. This is true. Associativity holds for rational numbers under multiplication. That is also true. What is the identity of the group? The identity of the group is 1. And the inverse of each element, if you take an arbitrary element A, which is the positive rational number, then its inverse would be, so you have to multiply, because the operation here is multiplication, by some number so that you get back the identity. So you will multiply obviously by 1 by A, and 1 by A is also again some positive rational number, so therefore this would surely be present in Q positive. So we would say inverse would exist for each of the element which is a member of this Q positive set. So therefore it forms a group. The next example is if we consider the set as the positive irrational numbers, and in addition to all the positive irrational numbers, we also take 1, and the operation that we take in this particular case is that of multiplication. So we are saying this is not a group. Why this is so? Because this satisfies associativity. It also has the identity, which is nothing but 1, right? But the inverse is also there for every element, but the closure is not satisfied, right? How this is so? Because why inverse is there? Because you see square root 2, that is a positive irrational number. If you take its inverse, what would be that? It would be 1 by square root 2, which is again an irrational number. So therefore inverses also exist in this case. But closure property does not satisfy, because when you multiply square root 2 with square root 2 only, you will get back 2, and 2 is not an irrational number. In fact, it is a rational number, right? So therefore in this case, this is not present in the given set of positive irrational numbers. So therefore this does not form a group, because the operation given is itself not a binary operation. For the next example here, we consider the set R star, which is that of non-zero real numbers. So all the real numbers except 0 are contained in this set. The operation here is multiplication. This form a group. Why? Because when you multiply two non-zero real numbers, that is again a real number, non-zero real number. When you also have associativity of real numbers under multiplication, no issue. Identity here is 1, and the inverse of each element A is also 1 by A. And the issue was with 0. If 0 was also present in this R, then 1 by 0, which is infinity, is not present in R. So therefore we have eliminated the 0 from our set. 0 is not there. So therefore it forms a group. For the next example, you see we have a set of integers, and the operation here is subtraction. So this does not form a group, because this is not associative. So you can check this quite clearly with the why this is not so, because it is not associative. So you can check this example, and there are so many examples for groups. You can look out and create look out for more examples and create your examples by yourself. So I'll be giving you more examples in the next video. Until then, you can try and create new examples of your own. Well, that is it for this video. Thank you for watching.